Thanks for the opportunity. I'd like to talk to you today about a new method to identify splice-altering variants from whole genome sequencing data. So this is, let me find my pointer, a method developed by Steve Monga in the lab, who's currently in Australia. Okay, we heard about splicing and aberrant splicing yesterday from Julian, but briefly, splicing is a process where introns are removed and exons are joined together. It's a complex process. It's mediated by the spliceosome and it's guided by motifs. So there's motifs along the region and the donor exon boundaries, the acceptor and donor motifs, and also there's motifs around silencers, enhancers, and also the branch point. And when there are genetic variants that occur within the region, that can lead into aberrant splicing because you can have exon skipping, intron inclusion, cryptic splice site use, and that can affect the resulting protein and potentially lead to a genetic disease. So it is important to be able to identify these variants to increase our genetic diagnosis. However, when we perform whole genome sequencing, we end up with millions of variants per individual. And as you know, the in vitro assays are very low throughput, so we have to rely on in silico predictions. And this is a difficult problem because the splicing code is complex. So one of the most widely used methods for prediction of splice-altering variant is Splice AI that was developed 4 years ago now by Illumina. And it was based on a deep neural network, and it did very well at it does very well at predicting cryptic splice mutations, especially in patients with rare genetic diseases. And since that method was available, there's been a lot of benchmarking studies, and we have also performed some benchmarking and have found that Splice AI performs better in comparison to the first generation methods for splice-altering variant prediction. And it has been used widely by many diagnostic labs, and we use it in our pipelines, but we are all identifying some accuracy issues. So for example, in this study where splice-altering variants in titin that can lead to cardiomyopathy were validated, and Splice AI was found to have very poor sensitivity for the validated splice-altering variants. So the problem is that in silico prediction can miss a lot of these variants entirely. And also we do end up having very large numbers of medium-low confidence candidates. So to tackle this problem, the Steve has been developing SpliceSM, which is a Python command line tool. The user provides a variant call format file and FASTA file, and then it outputs a score reflecting the variant's potential to disrupt splicing. It is based on an XGBoost classifier trained on known splice-altering variants, and it's still under development, but you can find it on our GitHub. So it's an ensemble model, so it integrates several established predictors. So obviously all the motif-based ones that Maxine Tiscan at ESRC and BPP. So these are for identifying variants that disrupt accepted donor motif or silencer enhancer motif, so the branch point. And it has two modes. You can use Splice AI, but also you can run it without that feature. And the main difference is that we use what we call the susceptibility maps. So these are regions of intrinsically high or low susceptibility to this type of variants. So these are based on what we call background sites, and these are sites that are found, they're unannotated splice sites that are found at low level in large RNA-seq repositories. And we use, we mine this 300K RNA data for this. And the reason for this, as I said, these are unannotated because splicing is actually noisy. So you do end up with many different transcripts, and some of them are due to errors during splicing. And it has been found that this background splicing that we find at low levels can be a predictor of aberrant splicing in genetic disease. So recently, there's been two new methods that use also RNA-seq information in different ways, and they have improved predictions of splice-altering variants. So our method is using this information a little bit differently. for predicted splice site gains, we intersect these sites with our data sets of these background sites, which is the low-level RNA-seq data. And we use this as a feature, the variant and the background site intersections. Another feature of our method is that it addresses the delta score pitfall, as it has been called. So basically, Splice AI returns a delta score, which is the difference between the score of the reference allele and the variant allele. However, there are situations where the reference allele actually has quite high score. So these are two examples of intronic regions where you have a high score for acceptor and donor motifs. And when you get a deep intronic variant here, these are increased. So this exon now is included, and this actually has a termination codon here, but the delta scores are very low. So these are actually missed by Splice AI. So our method is trying to address this problem by utilizing the raw scores of the algorithm. And then to see how what effect this might have, we calculated we've calculated the reference Splice AI score in unannotated splice sites across the genome, and we found more than 40,000 that have a score more than 0.5, and 84% of those are found in background RNA-seq datasets, and this means that they are susceptible to become splice site gains. So to evaluate our performance, we compiled a set of about 5,000 splice-altering variants and region match negatives. So these are usually from studies that have been found that have validated splice-altering variants. And we found that within splice sites, we perform better than Splice AI for both acceptor and donor sites. And we have removed the canonical sites because it's not trivial to predict. But we also do better for outside splice sites. And for these sites, I should say that we use an imbalance set to kind of depict more what we see in reality. And actually, a random predictor would do really, really badly. So in summary, we have developed a new method that is better than what we currently most variant prioritization pipelines use, which is Splice AI, and also it solves some issues in terms of coverage and scalability that Splice AI has, because it's very slow to run. So our method runs about 4,000 times faster. And we expect to be able to use it to better prioritize some candidate variants. I'd like to show you in the last 2 minutes, we have developed a new web visualization tool for splice altering variation that I encourage you to have a look, and we welcome feedback. So you enter your variant, and then you can see the scores for most of the splice altering prediction methods. So you can't really see it in the screenshot, but we've included a lot more than you can see. And there's functionalities that it has that I cannot show you in the screenshot, but yeah, I encourage you to have a look, and we welcome feedback. So thanks everyone in the group, especially Steve, who developed the method, and thanks very much.
Time for one quick question.
So surprise, surprise, I have a question. So thanks, very, very good. I didn't get the way you train the algorithm. Is it also based on this manually annotated variants?
Sorry.
And my question is essentially that there's the potential for the kind of ascertainment bias if we evaluate tools on things that have been reported in the literature, which themselves are using old tools, right?
Yeah, that's right. Actually, what we're doing, but I don't have the results to show you, is we are trying to evaluate splicing prediction algorithms using what we call a mutability adjusted proportion of singletons from NOMA database, where you calculate how many singletons. It's a metric that has been developed by the NOMA people, and you calculate how many singletons you expect, and that gives you you understand what I'm saying? Like whether there is a selection or not, and that can help you evaluate pathogenic variants in a genome-wide scale a lot better. But yeah, I agree with you. And we haven't actually used what you've done with RNA-seq
Yeah,
data.
so we called all those
Yeah.
advanced splicing and GTEx. The
Yeah.
sharing of the data requires you to have access to GTEx. It's a bit tricky
Yeah,
because those are private variants, but we can
Yeah.
talk if this is something you're interested in.
yeah, for sure. Yeah.